Today we're talking about parametric equations and arc length in Chapter 9. We want to be able to find arc lengths of curves given by parametric equations. And in this first example, we see that we have parametric equations can be used to describe the path of an object moving in a plane. This leads us to ask the question, how far has the object traveled? And a particle moving along a curve in the plane with a parametric equations where x is f of t and y is g of t, where t is the time, has the speed given by this formula right here. This is our speed, absolute value of velocity, and that's going to be our average rate of change. We can also find the distance traveled by the object moving along the curve between 2 points A and B by integrating speed, and that's going to be the distance traveled. That's our instantaneous rate of change. So we need to assume the object never stops or reverses its direction as it moves along the curve, and then the distance traveled is the length of the curve. So let's jump right in with some examples here. An equation in the form y equals f of x, where x is between 2 points A and B inclusively, has an arc length L of such a curve is given by the definite integral below. That's this formula right here. We want to use that formula to find the arc length from 0 to 3, given our function 4x to the 3/2 power divided by 3. So if we simplify this, we can get 8x to the 3/2 over 3. And the derivative is 4x to the 1/2 power. So next we want to substitute using that formula. The arc length is that integral from 0 to 3 of 1 plus f prime, which is 4 square roots of x squared under the radical with respect to x. So that arc length is going to be from 0 to 3, square root of 1 plus 16x dx. And using u substitution here, we could say u is 1 plus 16x. So du is 16 dx, and 1/16 du is dx, and then changing our bounds, the u of 0 is 1, and the u of 3 is 49. So we have a new integral, 1/16 from 1 to 49, u to the 1/2 power du. So that's going to give us 1/16, and this would be 2/3 u to the 3/2, evaluated from 1 to 49, and 2 divides, this is 16, not 18, 16, 2 divides 16, 8 times, so we got 1 over 8 times 3, that's 24, and we got 49 to the 3/2 power minus 1 to the 3/2 power. So the square root of 49 is 7. Let's see, cubed is 343 minus 1. That is 342. So we got 342 over 24, or let's see, I believe 6 divides that, so 57 fourths. 57 fourths is the arc length from 0 to 3 on that curve. Arc length in parametric form says if we have a smooth curve C given parametrically, such that C doesn't intersect itself on the interval from A to B inclusively, except possibly at endpoints, then the arc length of the curve over the interval can be calculated by any one of these formulas. So we'll apply that with a Randy the Roach question. If Randy the Roach is moving in the xy plane at time t, his position is given by the parametric equations where dx dt is 3t and dy dt is t squared. And we want to find the distance that Randy traveled from 0 to square root of 15. So that distance is the integral from 0 to radical 15 of 3t quantity squared plus t squared quantity squared under the radical with respect to time. And cleaning that up is going to give us the radical of 9t squared plus t to the 4th dt. And using u substitution, if u is, let's see, well, first we want to do this. We can rewrite this to be, let's see, take out the absolute value of t and t squared plus 9 dt. Then we could let, let's see, we'll let u be t squared plus 9 and du is 2t dt. So we have 1/2 du is t dt. And the u of 0 is 9. So the u of radical 15 is, let's see, 24. So rewriting our integral, we have 1/2 from our lower bound 9 to our upper bound 24, u to the 1/2 power du. And that's going to give us 1/2 times 2/3 u to the 3/2 evaluated from 9 to 24. So we have 1/3 and the radical 24 cubed minus radical 9 cubed. So let's see, we got 16 square roots of 6 minus 9, because let's think about this, 24 is 6 times 4, 6 times 4 under that radical. So we got 2 radical 6, and we're dividing by 3. Cubed. Cubed, so that's 8 over 3 radical 6 minus 3 cubed, that's 27. That's 9. For u to the 3/2. 48 radical 6. So just checking on this, 24, square root of 24 cubed looks like a 24 outside divided by this 3. and another 4 times 6, so that's 4. Radical 4 is 2. So this is 8 times 2, which is 16 square roots of 6. And this is 9. So the square root of 9 is 3. Cubed is 27. Divided by 3 is 9. And then if you needed a decimal approximation, you got around 30.1918 for the distance Randy traveled from 0 to radical 15. In example 3, we want to find the length of one arc of the cycloid with the parametric equations. X is theta minus sine and y is 1 minus cosine. So one arc is usually from 0 to 2 pi. So we would want L is the integral from a to b of dx dt squared plus dy dt squared with respect to time, all under the radical. So we're going to use that formula. And putting that together, we're going to go from 0 to 2 pi. We've got dx dt is going to be 1 minus cosine theta squared. And this is going to be positive sine squared theta d theta, using this formula here. And then cleaning that up, we've got 0 to 2 pi, and expanding this out would give us 1 minus 2 cosine theta plus cosine squared theta plus sine squared theta. And there's our identity that we can combine. So this piece right here is going to be equivalent to 1. So we can add those together. Whoop. From 0 to 2 pi. So we've got 2, 1 and 1 is 2, minus 2 cosine theta d theta. And jumping over to our calculator, let's go grab our, we've got menu, calculus, an integral from 0 to 2 pi. And we've got square root 2 minus 2 cosine theta. Whoop. D theta. Well, and the arc length has a measure of 8 units. So using our calculator to come up with that estimate or exact value on the cycloid. Here in example 4, we're looking for positive time. A particle is moving along a curve, so its position at time t is x of t, y of t, and x of t is shown in the graph. And for the particle y of t is x t squared, and we want to find the speed of the particle at time equals 1. So pulling from our formulas that we previously discussed, we've got the speed is the absolute value of velocity, and that's our formula dx dt quantity squared plus dy dt quantity squared. And we're looking at the picture over here, and it looks like we're looking at time is 1. So at time is 1 right here, the x prime of 1 looks like a rise of 5 and a run of 2. So we've got a slope of 2.5 there. And then we want to think about if y of t is x of t squared, then y prime of t is going to be x prime t squared times 2t. And we want y prime of 1. So the y prime of 1 is going to be x prime of 1 squared times 2 times 1. And the x prime of 1 is 5 over 2 times 2. So our y prime of 1 is 5. So we know the slope for 1 on x and the slope on y. And then finally, to put all that together, if we want the speed, absolute value of velocity at 1, using our formula up here, we've got 5 over 2 squared plus 5 squared. So that's looking like 25 fourths plus 25, which is 25 fourths. So 125 over 4 under the radical, which could be 5 square roots of 5 over 2. So we're finding the speed of the particle at 1 using our graph for the slope here at 1, and then using the formula y of t and the chain rule for that derivative. Here's a table problem. At time t, the position of a particle moving in the xy plane is given by the parametric functions x of t, y of t. They're giving us dx dt and y of t. And the function f of t is continuous and differentiable with selected values shown in the table below. We want to find the distance traveled by the particle from 1 to 5. So we need the derivative of y with respect to time, which is our y prime of t. And we got radical 3 f prime of 2t with the chain rule, so 2. So our derivative is going to be 2 radical 3 f prime of 2t. So we need this derivative. And then to find the total, we want the total distance traveled. So the total distance from, let's see, we're looking from 1 to 5. So the total distance is going to go from 1 to 5, and it's going to be the absolute value of the velocity with respect to time. So that's going to be 1 to 5 under the radical, and we've got x prime of t quantity squared plus y prime of t quantity squared dt under the radical. That's one of the biggest mistakes, is to forget the radical there. So just be very careful. So from 1 to 5, what was our x of t? Was 2 f prime of 2t quantity squared. And we found our y of t was 2 root 3 f prime 2 root 3 f prime of 2t quantity squared under the radical dt. So from 1 to 5, we've got 4 f prime of 2t. pull that 4 out, squared. And let's see, this could be 2, that's 4 times 3, that's 12. We can pull the 12 out. And f prime of 2t squared. That's convenient. So we have 12 and 4, so that's going to give us 16. F prime of 2t quantity squared dt. Taking the square root of 16, we've got 4. 1 times 5. And the radical cancels the square, so f prime of 2t dt. So we've got 4 times 1/2 f of 2t, evaluated from 1 to 5. So this is going to be 2. And we could evaluate from the f of 10 to the f of 2. And looking back at the table, so we need to know the f of 10. F of 10 is 9. And then the f of 2 was 3. So 2 times 9 minus 3, that's 6. 2 times 6 is 12. So a little tedious, but workable there. And then one last example. At time t, the position of a particle moving in the xy plane is given by the parametric functions x of t, y of t, where the derivative of x is here, and the graph of y consists of 4 line segments shown below, and when t is 0, the particle is at the point 4, 0. Okay, so we want to know, find the slope of the line tangent to the path of the particle at t equals 3. That's part A. So at t equals 3, the slope looks like it's -2. So dy dt at t equals 3 is going to be -2. And the slope of the tangent line is going to be dy dt divided by dx dt. And dy dt is -2. And dx dt is, what was that? T squared plus sine of t squared. So 3 squared is 9 plus sine of 3 squared, which is sine of 9. So we have this, and using our calculator, we can get a decimal approximation to be roughly that, slope of the tangent line. And we want to find the speed of the particle at 3. So speed is the square root of x prime of 3 quantity squared plus y prime of 3 quantity squared. And we had x prime of t was 9 plus the sine of 9 quantity squared, and the y prime of 3 was -2 squared. So grabbing our calculator here, we've got square root 9 plus 9 sine, I'm just using x, 9 plus 9 sine 9 squared plus 4. And we've got about, whoop, I got a different answer on my key. Hold on here a second. We have the wrong value here. That's not supposed to be in there. An extra 9. Something went wrong. That's not there. Okay. There you go. That's the right answer. 9.6222. Okay. So our speed is about 9.6222, and they're not giving us any units. And then part C says find the position of the particle at 3. So when x is 3, we have, they say x would be the initial plus the distance traveled from 0 to 3 on x prime of t dt. And we knew x of 3 is 4, and then again calculating the area from 0. So menu 4, 3, we want from 0 to 3, and our x prime of t was x squared plus the sine of x squared, dx, 9.77356. So 9.773562. So adding 4 to that, we've got 13.7735. So we knew the x of 3. So we knew when the y of 3 was 4, we were given that. The y of 3 was 4. So we know at time 3, the particle is located at 13.7735 and 4. And then finally find the total distance traveled by the particle. Oh, this is not the question on my thing. Find the equation of the line tangent to the path of the particle at t equals 3 is what my notes say. So let me go change this prompt. Okay, so we want to find the equation of the line tangent to the path of the particle at t equals 3. So we know 4 is the y value, and using the tangent line equation, we'll have y equals 4, and our slope of our tangent line from part A was negative 2.1249. So 4 minus 2.1249 times x minus our x value. So we had our ordered pair and our slope, 13.7735. So equation of the tangent line. And that's the end of lesson 2. See you next time.